So today we're going to look at probability. So probability is the likelihood of an event. What is its likelihood that it's going to happen? It is a numerical value that's measured from 0 to 1. 0 meaning that it is not going to happen at all. There's no way, it doesn't even exist. A possibility doesn't even exist, to 100% or 1. It is absolutely going to happen. It is the only thing that can happen. So what's the probability of drawing a red marble out of a bag of green marbles? Not going to happen. Versus what's the probability of drawing a red marble out of a bag of red marbles? It's the only thing that can happen. And then you've got different levels in between. 50% or 0.5 would be, it's equally likely. You could choose, you could have heads or tails. So it's equally likely. There are a couple of things that you need to know, some important things. All coins, we will assume that they have two sides. Dice, typically, what we will use for our assumption is that a dice will have 6 sides, numbered 1 through 6. And a standard deck of playing cards has 52 cards. There are 13 cards in each suit: hearts, diamonds, spades, and clubs. There are 26 red cards and 26 black cards. And there are 12 face cards, anything that would have a face: a jack, a queen, or a king. So we're going to focus on experimental versus theoretical probabilities. So the definition of experimental probability is the number of times the event actually occurs and the number of times the experiment was done. So you actually do an experiment and you actually keep count of the number of times that things happen. And so your key words are going to be that they took data, right? That they did an experiment, or that they counted this many things out of this many times. Versus theoretical, which is the number of favorable outcomes, just generically, how many things that can happen that I want to happen over how many things can happen. I want red marbles, I want green marbles, there are red and green marbles in the bag. Okay, the sum of the probability of an event happening and the probability of it not happening is 100%, right? It's either going to happen or it's not going to happen that way. And the probability of it not happening is the complement. So the two numbers would add up to 1. So if you had a 20% of it happening, then you have an 80% chance of it not happening. And they have to add up to 1 or 100%. So let's look at some examples. We'll start here with experimental, and you can see the difference. A quality control inspector samples 500 LCD monitors and finds defects in 3 of them. So that is an experiment. He has a certain sample of things, and a certain number of things happened, right? If the company manufactures 15,240 monitors in a month, how many are likely to have a defect based on the quality inspector's results? Okay, so what we want to do is we want to take a small piece of data and we want to extend it to predict a larger piece of data. There are a couple ways you can look at this. If you look at what's the experimental probability, it's the number of times the event occurs versus the number of times the experiment is done. So there were 3 defects out of 500. Okay, so 3 out of 500, 3 out of 500 is 0.6%. So there is a 0.6% chance of choosing a monitor that has a defect. So what we want to do is apply that percentage now to this total number and say, well, okay, then if we take 15,240 and multiply it by 0.006, then we can predict that about 91 monitors are going to be defective. Okay, now another way of this is in proportion. If 3 out of 500 were defective, then how many will be defective out of 15,240? And that's the same thing. You're just taking this ratio, right? That's your scale factor, and you're multiplying it by the number of articles that you have, and the number of things that you have. Okay? Now, we can also extend this to, we know that the probability, we've determined that the probability of selecting a bag from a bag of marbles that has 12 marbles, we have green, blue, or red. The probability that randomly selected marble is green is 1/3. So we know the probability, we've already been given the probability that it's green is 1/3. The probability of it being blue is 1/2. So we want to anticipate how many of each color marble are in the bag. So we have already determined our probability, and so what we can do is apply that probability to the number of events that we have, and we have 12 marbles, so 1/3 of 12 is 4, so we can anticipate then, if everything holds true, that there are going to be 4 green. Half of the 12 is 6, that there are going to be 6 blue. If there are 4 green and 6 blue, then that means that there have to be 2 red so that we can total the 12 marbles. And so that is how you can take probabilities and extend them and anticipate then what is in your sample set. Okay, now those are experimental probabilities. So theoretical probabilities. So this is what a theoretical probability looks like. It's all the things that you want to happen, the things that make you happy, that are considered a success, over all the things that are possible. So, for instance, what's the possibility of throwing tails when you toss a coin? Well, there's 1 tails out of 2 sides, so the probability is 1/2, or 50%. Theoretically, but we all know that if you flip a coin 10 times, you might flip tails 8 times out of the 10. Okay, the 8 out of 10 is the experimental probability. The 1 out of 2 or 5 out of 10 is the theoretical probability. Okay, so that's the difference between them. So a marble is drawn from a bag that contains 4 blue, 6 green, and 3 yellow marbles. Now this is just predicting what we think will happen. It doesn't mean that it's going to happen this way every time. So what's the probability that I'm going to draw a yellow marble? Well, there are 3 yellow marbles in the bag. There are 13 marbles in the bag. So I want to know what's the probability of what I want. I want yellow. How many yellow events are there out of how many total events are there? Now we can write our probabilities in fractions, like 3/13. We can write it in decimals, which would be 0.231, or we can write it in percent, 23.1%. Now, what's the probability that it's not yellow? Well, if it's not yellow, that means it's blue or green. So I don't care, but not yellow makes me happy. 10 marbles in the bag make me happy out of 13 marbles. Well, notice that 3 out of 13 and 10 out of 13 add to 13 out of 13 because it's either yellow or it's not yellow. These two are complements of each other. So 10 out of 13 is 0.769, or 76.9%. These two add to 100%. It's either yellow or it's not yellow. It's yellow or it's another color, right? So they add to 100%. 100% chance it's going to be one or the other. Okay, so this would be the complement. So if you're asked for the complement, you find the difference between the probability that you know and 100%. Okay, now what's the probability of rolling a die? Again, we're going to assume that we have 1, 2, 3, 4, 5, 6. We have a standard cube, number cube. Okay, and what's the probability of rolling a 3? Well, there is 1 3 on the dice, and there are 6 sides. So my fractional probability would be 1/6. What's the probability of rolling an odd number? There are 1, 2, 3 odd numbers, numbers that are not divisible by 2. 3 numbers are odd out of 6 numbers in all. And what's the probability of rolling a 7? Well, there are no 7s, so I cannot roll a 7. So there is a 0% chance, or a 0 out of 6 chance, that I am going to roll a 7. Okay? Now, what if you roll 2 dice at the same time, a white dice and a black dice? Now, this is incorporating all of them, right? A white 2 and a black 1, and a black 2 and a white 1. So it includes all of them. There are 36 possibilities, right? This is a 6 by 6 table that includes all the possibilities. So what is the probability that you will roll numbers that add to less than 5? So what you want to go through and do is count all of the occurrences that are less than 5. So 1 and 1, 1 and 2, 1 and 3, 1 and 4 is 5. 2 and 1, 2 and 2, 2 and 3 is 5. 3 and 1, 3 and 2 is 5, 1 and 4 is 5, and so that's it. That's all we've got. Those are all the possibilities of rolling the dice, including the black and the white dice, whichever one the number is on. So there are 1, 2, 3, 4, 5, 6 that are less than 5 out of the 36 possibilities that there could be. That is a 1 out of 6 possibility. The probability is 1 over 6, or 16.7%. Typically, I will have you write answers as decimals, or as percentages or fractions, because I think those make the most sense to you, particularly percentages, because you're so used to your grades being in percentages. So that's usually how I'll ask you how to do them. Okay, now let's look at cards. Given a full deck of 52 cards, what's the probability of drawing a face card? There are 12 face cards out of 52 cards. And 12 out of 52, remember your calculator can reduce the fractions for you. 12 out of 52 is 3 out of 13. So 3 divided by 13 is 23.1%. And what's the probability of drawing a red card? Remember that there are 26 red cards out of 52 cards. So it is, my probability is 1/2, or 50%. Okay, so I have, if I do it 2 times, then I will probably pick a red card 1 out of the 2 times. That's what should happen, theoretically. But we all know that we can draw 2 red cards in a row. Okay, even though technically you should draw a red and then a black if probability fits. Okay, now let's put this all together and look at this last one. A student randomly selects a card from a set of 10 cards numbered 1 to 10. So I have those numbered over here. She notes the number on the card and places it back in the deck. She repeats this 20 times and finds that she chose a prime number 6 times. Explain how the student's experimental probability of choosing a prime number compares to the theoretical probability of choosing a prime number. So her experimental probability is how many times it actually happened. So she chose a prime number 6 times out of 20 times of repeating the experiment. Okay, 6 times she chose a prime out of 20 times that she drew. So 6 out of 20 reduces to 0.3, or 3 out of 10. So she had a 3 out of 10, or 30% chance of, with experimental probability, 30% of the time, she chose a prime number. Now, let me remind you what a prime number is. 2, 3, 5, and 7 are prime numbers. 1 is neither prime nor composite. Prime means that the only thing that goes into it is 1 and itself. Okay, so every other number has multiples that go into it, like 4 would be 4 and 1, or 2 and 2, for example. So that's what a prime number is, just a reminder. So the theoretical probability then, given this set of numbers, theoretically then, there are 1, 2, 3, 4, right? There are 4 prime numbers out of the 10 numbers that there are. So what we can see here is that her experimental probability is lower than her theoretical probability. Theoretically, she should have a probability of choosing it 40% of the time, or she should choose a prime number 40% of the time, but experimentally, she actually only chose it 30% of the time. Okay, now, if we want to just summarize this, give a possible probability for an event that is impossible. It cannot happen. That is 0. Okay, if we go all the way to certain, then that is 1. 100% it's going to happen. Then everything from there is some span from 0 to 1. So very unlikely. Might be maybe 0.1. 10% chance, 0.05, something small. Somewhat unlikely. Maybe 0.3, 0.4, something like that. A little bit closer to half, more than halfway between not impossible and equally as likely. Equally as likely as not, that's 50%, right? It can happen or not happen, heads or tails, okay? Somewhat likely, maybe a little more than half, zero point 0.6. Very likely, not quite 100, but maybe 0.9. And then certain. So they're going to span. So that impossible is 0. Your equally as likely is 0.5, and certain is 1. And everything else falls in between and goes, somewhere closer to any one of those numbers depending on where we want to be. Okay, so experimental probability is the number of times the event occurs divided by the number of times the whole experiment is done. And then theoretical probability is the number of things in the set of numbers that you're looking at that you want divided by the whole number of possible outcomes.